Hello everyone. Today we're going to be discussing the balance equations in thermodynamics. Now, why are these balance equations very important? It's because they help you understand how to analyze every single part of your system. So, if you remember from last lecture, I mentioned something about E in is equal E out. So whatever this is energy input has to equal to energy output. So whatever you put into your system, there is something that's going to come out, right? Whatever is coming in is coming out. Like there's always a balance. You can't put something and just like get nothing out of it, you know? So how do we understand that? How do we balance out our systems? I'll give you this turbine here as an example. So we have an input. So say this is state 1, and we have an output, state 2, and we have WT, work turbine, right? Turbines basically work, you have a higher temperature steam coming in, it comes in, it spins the steam, the turbine's blades, and you have a lower temperature steam exiting the turbine. So how do I analyze this turbine, right? We use balance equations. So we're going to go over the mass balance equations, MBE, which pretty much discusses what is happening in the system when it comes to mass, whether it's mass flow, whether the mass is constant inside a turbine. Now, from what you can see here, if we put a really neat boundary here around the system, that is what I'm analyzing right now for the balance equations. You can see that I have this one here crossing in, 2 is crossing out, WT is going out also, it's crossing the boundary. So when it comes to balance, all we have flowing in and out is mass 1 and mass 2. So for the input for En, m dot 1, m dot because it's a flow, remember that, it's an open system. So we have a constant volume in here as long as m dot 1 equals to m dot 2, right? So the only inputs that we have when it comes to mass is m1, right? There's nothing else going into the system. We put an equal sign. Now what is coming out of the system when it comes to mass? 2, right here. So m dot 2, right? Now that's it. Our mass balance equation. What does that tell us? It tells us that m1 is equal to m2. And that is basically what's happening. You have a flow coming in and it goes out, right? Like nothing, like there's no leaking here. There's no like m3. There's none of that, right? So m1 equals to m2. Very basic, very simple, straightforward. Now we're done with our mass balance equation. I'm going to do other examples too, other than the turbine. However, let's move on to the energy balance equation. This is very important. This pretty much tells you what is the thermodynamics that is happening inside of your part. So in here, we have a mass flowing in, which carries with it enthalpy, right? It carries with it specific enthalpy, H. So this mass coming in, we can multiply it, m1, m dot 1, multiply by h1. So the enthalpy here at this state 1 flowing into the system, it's carrying its enthalpy energy with it into the turbine. So we have an h1, right? Now, are there any other inputs to the system when it comes to energy? No, we only have enthalpy here, and there's an output for enthalpy here, and there's an output for work, right? So there's no other inputs, we put an equal sign. Now, when it comes to the second, like the outputs, right? What are the outputs? We have WT, work turbine, and we have M2 H2, right? Because it's an enthalpy, there's a flow happening. So M dot 2 H2. That's our flow outside of the turbine. Plus, what's this? Work output of the turbine, right? Now, if you know the work, the flow, right? The mass flow for the turbine, and of course you know that m dot m1 dot is equal to m2 dot, right? Which means that you can also figure out the work of the turbine if you know the temperature at state 1 and the temperature at state 2, and you need pressure also, right? So if you have isentropic, it's a long process. It kind of gets like is a little weird at the beginning to go through the thermodynamic tables. I'm gonna go over that in another video. However, it is very, very simple. It's just all you need is a couple, like a little bit of information. You can figure all of this out and you can find the work of the turbine itself. That's why we use the balance equations, because it helps us analyze and find values that we want, right? So we did our analysis here on this turbine. Let me give you another quick example, right? So again, we said that E in is equal to E out. Whatever comes in equals to whatever comes out, right? So if I give you this here, this mixing chamber, right? So I'm gonna call this 1, 2, 3, 4, right? So as you can see inside, I didn't specify whether there's like a line like between M1 and M3 that say they are not connected. This is just a mixing chamber, so it's an MC. And actually, let me write with a better color. So just a mixing chamber, right? It's not a heat exchanger. There is literally mixing happening inside. It's not that each pipe is connected to another pipe. So in this case, if I put here a boundary around this, right, around this mixing chamber, I can analyze it using the balance equations, right? So let's start with the mass balance equation. So we know that this is an open system, right? Because it's open, mass is flowing, right? So volume is constant inside as long as these flows are equal. Whatever is coming in, whatever is gonna go out, right? So if looking at our boundary here, what are the inputs when it comes to mass to this system? We have M1 and M2, right? M1 and M2. So we can write simply M1 dot plus M2 dot, right? There's no other inputs when it comes to mass in here. So we put an equal sign. So now we're talking about the E out. We already mentioned the E in, what's happening, what's flowing into the system. Now we gotta understand what is flowing out of the system when it comes to mass. What is flowing out? 3 and 4. You can see the arrows pointing out of the system, right? They're crossing the boundary. So M dot 3 plus M dot 4. That's our mass balance equation. This is what's coming in when it comes to mass. This is what's going out when it comes to mass. Now let's move on to the energy balance equations. Now remember, when there's a mass flow, there's enthalpy. So what is coming into the system when it comes to energy? M dot 1 H1. What about 2 right here? It's also flowing into the system. M dot 2 H2. And you can actually look up there. You can see it's very, very similar, right? Very close. It's just that we're talking about enthalpy here. We're talking only about mass. Now, why do I multiply mass with enthalpy? It's pretty much just unit analysis. Like, so mass is kilogram per second, right? And enthalpy is kilojoule per kilogram. So kilogram cancels with kilogram. We'll end up with kilojoule per second, which is essentially kilowatts, right? So it's just unit analysis. You can literally take these out if you want, but I like to keep them to get a final answer in kilowatts, like specifically, you know, so I know my units. I stick to that all the time. Now, we mentioned what is flowing into the system when it comes to energy. There's nothing else, right, in the inputs. Put an equal sign, right? Let me just put this in a box here in the corner. What about the outputs of this mixing chamber when it comes to energy? We have state 3 and state 4. So M dot 3 H3 plus M dot 4 H4. This is our outputs. E out. There's nothing else, right? It's very simple, very straightforward. I can actually give you another example on this one, so you would understand the difference. Like, you would really understand balance equations by the end of this video. So let's make another example. I'm gonna put a heat exchanger here because honestly, myself, I used to mix them up a lot. Like, I didn't know the difference between a mixing chamber and a heat exchanger when it comes to balance equations. So I have an input here, a flow, right? and this is going in here at 1, flowing out at 2, right? Actually, I don't want to circle that yet, right? I have another input here, and this is 3, 4, right? 3 and 4. Now, as you can see, this is a heat exchanger, right? So you can tell that this flow is coming in 1, it's going through and exiting at 2, right? This is 3 coming in, flowing, going to 4. So 1 and 2 are not mixing with 3 and 4. They're just flowing in separately. There's no mixing happening in here, right? So what does that tell us, right? Well, it tells us a lot when it comes to the balance equations, right? So I'm gonna put this border right here. Actually, let me choose a better color. Um, Crap, let me get some other color. Maybe the yellow. Yep, yellow actually is good, right? So, how do I analyze this when it comes to mass balance equations and energy balance equations? So, MBE, again, I'm gonna write this here. E in is equal to E out, right? Whatever's flowing in is whatever is gonna come out, right? They have to be equal to each other. Now, M1 is flowing in, right? And what does M1 equal to? So if M1 is flowing in here, it's going through this pipe and it's coming out. So M1 is equal to M2, right? Because M1 goes in here and ends up at here, too. Now some of you might think, no, why don't we put this and we didn't put M1 plus M3 is equal to M2 plus M4. Well, the reason we don't put this is because M1 and M3 are not mixing. This is different. However, the correct way to say is M1 is equal to M2, and we'll put here an apostrophe, a comma, right? M3 is the input, is equal to M4, which is the output of that flow in here. So this down here is wrong, right? Because M2 and M4 are not mixing. M1 and M2 are the only ones that are going through together in this flow, and M3 and M4 are the ones that are going together in this flow in here. So you can't say M1 plus M3 is equal to M2 plus M4. This is completely wrong, right? So that's just conceptually, you have to understand that. So let's discuss the energy balance equation for this one, right? Now, what is coming into the heat exchanger and what is going out? M1, H1, right? This is the enthalpy that is hitting into the exchanger. So there's energy happening in here. There's an energy flow in here. Enthalpy is happening in this heat exchanger, right? Lots of enthalpy from this entrance. Same goes to here, M3. There's enthalpy, right? Which means that it's plus M3H3 because this is enthalpy and we're not talking about mass flow anymore. These pipes, they only tell you like the mass, what's happening to the mass. M1 is going to M2, right? And this will make a big deal right here. Some of you might think that it's not a big deal, but it is. Why did I put them like in different boxes, right? There's a comma in between because say M1 is like 10 kilogram per second, M1 and M2, but M3 and M4 are 20 kilogram per second, right? That can't be correct when I put M1 plus M3 is equal to M2 plus M4 because we're different now. M1 and M2 are equal, but M1 plus M3 is not equal to M2 plus M4. You might have different flows, so you need to make sure that you understand what's going on inside of the heat exchanger, specifically when it comes to the flow. However, when it comes to energy, energy spreads out into the system, right? So we don't really care whether it's coming from this flow or from that flow, as long as my boundary is around here. My boundary isn't inside here. My boundary isn't comparing this pipe to that pipe, right? My boundary is talking about this entire thing around here, right? And I know that there's an M1H1 coming in. There's an H1 enthalpy here coming into the system, and there's enthalpy here coming into the system, right? So that's all I care about when it comes to the inputs. So those are the only two inputs, right? So put an equal sign. What about the outputs? M2H2 plus M4H4, right? Pretty straightforward. That's the output. That's the output. Output H, H2, output H, H4, right? Here it's 1, and here it's 3. So again, going with a really quick summary, balance equations, right? Balance equations help you analyze the systems that you have in your cycle, say, right? So usually you'd have a big cycle, like let's say here I'm gonna draw a real quick cycle. Let's make a compressor, right? Air comes in, and then this compressor, after the air is compressed, it goes into a combustion chamber, and fuel is provided in, so I have a Q input, heat, right? And then this flow comes out, right? This air is hot now, goes into a turbine. It spins the turbine blades. I have WT, right? And there's WC here. That's the compressor work input. That's how much compressors need to operate, right? And there's an excess here, what's coming out, right? So basically, a cycle like this, now you can analyze it because you can look, oh, that's a compressor. Well, compressor is, there's probably an input, so probably we'll call that like 1, and then here it's 2, and the input is WC, right? When it comes to the work, you need work to get this compressor to work, right? So we put H1, what is the other input? Plus WC, this is for the compressor, equal to H2, right? It's very simple. Now you can analyze any system, any device that you have in your system, right? Same thing goes with a turbine. H, let's call this, so this is 2, 3, and 4, right? So H3 is going to equal to H4 plus WT, the work output of the turbine. Done. We have the EBEs for both the compressor and the turbine, right? So you can figure out your values, whatever you're missing, whatever you need to find, you can figure out using the balance equations. And make sure you understand the mass, because the mass also relies heavily, even the energy balance equation, they both rely heavily on the boundary. So wherever you put your boundary around your system is what you are understanding, is what you are analyzing. And usually when you're analyzing a piece of your cycle, you want to analyze the entire thing. What is flowing into it? What is it flowing out of it? I hope this was helpful for you guys. I actually wanted to include more examples, but I thought that the video would get like too long and you might get bored. Thank you so much, and as I always mention, please leave feedback for me because I really need your feedback. I'm new to this. I'm trying to make like the best videos I can ever like make for you guys. I really want you to understand thermodynamics. It's very simple. Professors usually tend to overcomplicate it. Thankfully, my professor didn't, and I just want to spread the word. I want to teach you how my professor taught me. Thank you so much, and I hope to see you very soon. Bye-bye.